So, okay, so here we are. So today, what I want to talk to you about is I'm using the abbreviation carbon-13 NMR. Okay. So let me give you, I'm going to start with some introductory information. And in the advanced NMR lecture, which the first part of it is recorded, and in that first part, there's notes and a recording. This will be covered in more detail, but so we've already done some NMR stuff, and we talked about all of these characteristics of NMR. We talked about equivalence, and we talked about integration and chemical shift and splitting. But when we were doing this, we were looking specifically at what we might call hydrogen 1 atoms, by which we mean the isotope of hydrogen that literally has only one particle in its nucleus, that particle being one proton. Okay. And that is fine. We saw that there's a lot of use to that, but hydrogen 1 is not the only NMR active atom. And I say atom isotope because I'm going to show you what happens with carbon. And then in the advanced NMR lecture that I put up there, I'll explain to you in more detail what has to be in a nucleus for it to be able to be NMR active. So not all isotopes are active even of a given element. Okay. Excuse me. And hopefully you guys remember what isotopes are, but isotopes are atoms of an element that have different number of particles in the nucleus. So for example, carbon has 3 isotopes that we generally see. Let's say 3 stable isotopes, because at least in theory, we can manufacture a number of different isotopes, but a lot of them are really unstable and they basically decay. They do radioactive decay and they break apart almost instantly. But carbon has 3 that are reasonably stable. We can make samples of them. We can do chemistry with them. Okay. So the first one is the 12 isotope. Okay. We would call this carbon 12. And the 12 isotope, and I didn't even know, in the nucleus has 6 protons and 6 neutrons. And so we add those up. That's where we get the 12. The technical thing is 12 over 6. Okay. The 6 for carbon never changes because it's the bottom number, the number of protons, that determines the identity of the element. Okay, so we're going to see that in just a minute, but the number of neutrons can change. And so what we see then is we also have carbon 13 over 6. We call that carbon 13. Still 6 protons, but 7 neutrons. So 6 plus 7 adding up to 13. And then actually there is also carbon 14 over 6. Still 6 protons, 8 neutrons. This one, okay, this carbon 14 is radioactive. It's not completely stable. So its nucleus breaks apart. It becomes the atom becomes actually a different element, and it gives off a radioactive particle. And I don't know the exact decay for that. I don't know if it's alpha decay or beta decay or whatever, but it's radioactive. So it disappears over time. It has a pretty long half-life, but it does disappear over time. The interesting thing about carbon 14, just really quickly so you understand it, is that carbon dioxide in the upper atmosphere gets bombarded with cosmic rays, and it gets converted it's a low rate, but it's a constant rate, gets converted to carbon 14, which then, because it's carbon dioxide, it comes down, it's incorporated into plants, then it goes into, you know, the ecosystem, and it gets kind of locked away. So like if, you know, I don't know, if a plant in the dinosaur times ate it or used it to make one of its plant things, and then a dinosaur ate the plant, and then that got used to make something in the dinosaur's body, and then the dinosaur died, and it, you know, it got buried and it became oil or something like that. That oil would have some carbon 14 in it. It's constantly being regenerated. And so that actually is the science behind carbon 14 dating. And so that's why carbon 14 dating works and continues to work. All of the carbon 14 from the formation of the universe or the formation of the planet has not disappeared because it's constantly being regenerated. Kind of interesting. All right, now what we're going to see next time is that to be NMR active, you have to have an odd number either of neutrons or protons or both. And in this case, carbon 13 has the odd number of neutrons. The problem is the abundance. In other words, what percentage of these things? And the problem is that carbon 13 is only 1.8% abundance. Carbon 14 is like 98 point something. I didn't look it up. And carbon 14 is also very low abundance, and I don't remember what that is, but okay, we can look those up. You're not going to be tested on it. If you just remember about 1%, that'll probably always be good enough. And the point is that if we look at a collection of molecules, only 1 in 100 of all the carbon atoms are going to be carbon 13, which means that a lot of those molecules might not even have a carbon 13. They might have all carbon 12s. The ones that do have a carbon 13 probably don't have a second carbon 13. So we usually expect only to find 1 carbon 13 in a given molecule. And it means that it's going to be way harder to see the NMR signals. They're way weaker in carbon 13. And so we're going to have to talk about what do we do? All right. So Having said that, though, carbon-13 would otherwise work pretty similar to the way that hydrogen-1 does. And so we will come back and look. We're going to be mainly interested in the chemical shift. But equivalence works the same way, right? This mirror image and substitution thing. We're not going to go over equivalence in carbon because equivalence basically works the same way. All right. Okay, so we're going to have to look at how do we even get a carbon-13 NMR? Okay, so this is going to be a little detour, but I want you to understand this concept, okay? Not transform. Okay, so it turns out that there are two types of NMR instruments, continuous wave and Fourier transform. I'm going to start with continuous wave. I know this seems very, very TMI, but it's relevant, and we're going to see this affecting our own instruments, okay? Okay, so this is the older technology. It's the way the original instruments were set up. I don't know if this is the best as what my brain is giving me as to explain it. So here's the deal. I don't need a whole NMR scale. I'm just going to put part of an NMR scale, but you can just imagine this. All right. So here's 0 parts per million. Here's 1, 2, 3, 4. Okay. Well, what's really happening is that we're putting in, where can I draw this? We're putting in radio energy and unfortunately, I've got to go look this up. Okay, I'm just going to make up numbers, but for example, let's say that at this we put in 3 million hertz. Hertz is the unit of frequency. It means oscillations per second. Okay, in other words, no, that's not right. 300 million hertz, sorry. This would be 300 megahertz. Now, it turns out that's not actually where 300 megahertz is going to be. 300 megahertz would be down here. We call that nu zero, nu being the symbol for frequency. But since I don't know what it would actually be, stupid computer freaking out. I don't know why. Since I don't know what it would actually be, I'm just going to say 300 million here. Now, it turns out that what happens is if we go to a parts per million of 1, that's actually shifted by 1 part per million, okay? So that would come at 300 million 0.00300 hertz. I'm sorry, it's not higher, it's lower. My mistake. 299999700. Okay. So that the difference here would be 300 hertz. Okay. Now, you're not going to be required to memorize these numbers. Just follow along with the example. And so the difference here would be another 300 hertz, 1 part per million, and so forth. Okay. So can you see that there would be like specific frequency numbers? Okay. So in a continuous wave spectrum, what we do is we have a radio frequency thing. So we set up our NMR. So this would be our sample tube. Okay. It's in a giant magnet. I'm just going to represent that. Okay, sample tube. That's the sample. This thing is a giant magnet. And then what we have is we have a radio frequency, God darn it, transmitter. So that's hooked up to something, and we can change the radio frequencies by turning a knob. And then, and this is going to be hard to sort of picture, but at 90 degrees to that, so there's a 90-degree angle between these two, we have a radio frequency absorber. Okay. Very diagrammatic top view here. What's happening then is we have this giant magnet. We have the sample here. We put in radio frequency, and then we look at what gets shot back out. Because what actually happens here is we blast the radio frequency in at this one angle, it gets absorbed, and then the sample starts emitting out radio frequency, okay, at only certain frequencies, okay? So then what we do is we turn the knob, we tune across the radio frequencies. And measure okay, can you visualize that? So it's literally like if you've ever worked with an old, see all the radios are digital now, but if you ever had an old radio, you'd turn the knob, you'd be scanning across the different possible radio frequencies, the different possible stations. When you hit one, you'd get a signal and you'd hear something. Otherwise, you just hear static, right? So, oh, I'm absorbing that. Then static, static, static. Oh, now I'm absorbing again. Does that make sense? So it's literally the way that it's the easiest way for you guys to conceptually understand. It's probably the way you would sort of say this is how it should work. You just scan across, you look at where it absorbs, then you put it on, you know, you put that on a piece of paper or into a computer or whatever. Those are my absorption frequencies. Okay? Questions about that? Now, continuous wave is great. Don't get me wrong. It works. The problem with continuous wave is that it's less sensitive, okay? It's less sensitive. Let me show you what I mean by that, okay? So when I was in college, I took a class on the theory behind electronic instruments, because you got to remember that electronic instruments really only started to be developed in the 1930s. And so, you know, I was in college in the 1980s. That was only 50 years before that. It was kind of considered still pretty cutting edge. Okay. Now you guys are in the, you know, 2020s, another 40 years later. Now it's almost 100 years old. Nobody cares. But basically, one of the things that they pointed out was that when you have an electronic instrument, like an RF scan, it has noise, okay? So noise looks like this. So the problem with noise is that as you zoom in on it, it starts to look like peaks. So then when you have an absorbance, it's just sticking out of the noise. Yeah, absorption. Absorbance. I always screw these up. I probably have this terminology wrong. I have to go look it up. Okay. okay? And what we see is that in continuous wave, they're hidden in the noise. Literally the technical term for that we say is buried. So here's our noise. There's our weak signal. Sorry, the noise should all be the same size. You see, okay? And I don't want to spend a whole lot of time on noise, but noise comes from various things. It comes from the fact that there's just random processes like radioactive decay, like cosmic rays from the sun, like, thermal emission. You know how, I don't know if you know this, but you can take atoms, you can heat them up and electrons will pop off if they're really hot. But actually, even at room temperature, there's some small amount of thermal emission, et cetera. So there's all these things, these random processes that unfortunately in our electronic instruments, they get interpreted as electrical signals. And so there's always noise. So if you go and you get your, I don't know what do any of you guys listen to music anymore anyways? But if you get whatever device you're listening to music on, you shut off the music, be careful, and you turn it way up, you'll hear kind of a hiss. That's basically noise. And it's basically the same thing, same kind of thing that the music is doing. It's just that it's very small and random, as opposed to music where they're putting out very specific frequencies at very high strength so that it stands out above the noise. All right, everybody cool with that? Noise, it's a problem. All right, so you can see that if, for example, you have a nucleus like this where only 1% of the nuclei are actually going to absorb, that means that your signals are going to be 100 times smaller. And it's actually worse. There's another effect that makes it even smaller than that. It's a big, it's this huge thing. So essentially, on a continuous wave instrument, unless it's a very, very strong instrument, the bigger the magnet, the smaller the noise compared to the peaks. But most instruments are hard to make that big. You're not going to be able to do carbon NMR. So what they did was they invented a new type of instrument, okay? They call it the Fourier Transform instrument, abbreviated FT. Now, this was only possible when they got computers. So the original instruments used electronic circuits that weren't computers. You can construct electronic circuits to do math, to scale things up, to show absorbances, but they're not computers. They're just hardwired circuits. So at that time, then all you could do is continuous wave. But once they got computers, they could make a more sophisticated instrument that could take a complicated signal, do computations on it, and convert it into something we can use, okay? All righty. So how does this work? So first of all, So stick with me on this. I'm just trying to write out what the picture is going to show you, okay? And it may not make sense at first, but as we play with it, it'll make sense. Okay, so excuse me. Give me a second here. It spazzed. Why did it spaz like that? Looks like a repeating wave, okay? So, so if we watch that over time, if this is our voltage, an electrical wave does this. It goes up and it comes down, and it goes up and it comes down, and it goes up and it comes down, okay? That's a wave. And the frequency is defined as so remember we said we're kind of looking at, so we're saying this is 0 seconds. Well, let's see. This is, we're going to do this in microseconds, okay? Pardon me, but okay. So this is 0 microseconds. We're going to do a frequency of, let's do 1 megahertz. 1 megahertz will be really easy. So this would be 1 microsecond. This would be 2 microseconds. Sorry. Okay. And so what we see is that the time for one complete oscillation so the frequency is equal to 1 over 1 microsecond, right? So it equals 1 million per second. Does that make sense? Equals 1 million hertz. Okay? I want you to just visualize that, right? And so what would happen if we had 2 frequencies going there? Same thing, okay? And I know this seems bizarre, but it'll really help you, even when you take physics or whatever going forward, it'll help you if you begin to sort of visualize. So we're going to set it up exactly the same way. Yeah, my scale is off because I didn't put it evenly because I'm a spaz. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So let's at least make it look more to scale. 2, 3. We have oscillating from plus to minus. That's what we are measuring. And I'm going to put my original frequency. So on my original frequency went up, came down, back up. Sorry, came down. Like that, okay? Now what if we put a second one that's twice as fast? Okay, well then that's gonna look like this. It's gonna come up, down, and back up. Then it's gonna come up, down, and back up. Then it's gonna come up, down, and back up. Like this. Does that, can you visualize that? But that's not actually what we're going to see. Because what's going to happen here is this number plus that number are going to add up. So for example, here where we have, both of them, we're going up really high, and then we kind of stay, and then we go down, start to go down, we go lower, but we don't actually get below zero, right? Then it starts coming back up, but we're coming up lower. And then you see, you get this, I can't do the whole pattern, but you see, you get this complicated pattern. Does that make sense? That's the combination of these. And that's not a very accurate picture of it, but you get, so we don't see the blue or the green. We see this complicated red. And it's like, what the hell is the frequency of that? It's going up and down. What's one oscillation? Does that make sense? Okay. So what do? Well, it turns out that what we can do with the Fourier transform is the Fourier transform can take the red wave and it can convert it, and it can say, okay, what we really have here is okay, this is the frequency in megahertz. So if you recall, the blue wave was 1 megahertz. Sorry, I meant to color blue. And the green wave was 0.5 megahertz. Okay, so it says this red wave is actually made up of this frequency plus that frequency. It can also, the size of the wave is called the amplitude. They aren't all the same size. It can also tell us like this wave was bigger and so forth. Okay, does that make sense? So we call this the time domain. And by doing a mathematical thing on the computer, we can convert it to the frequency domain. And the frequency domain is basically what we see in an NMR, right? If we look up here, what we're really doing, if we scan across the NMR, we're saying at this frequency, there's a signal. At this frequency, there's a signal. Do you see? Your continuous wave is always the frequency domain. And that's what we want. But what we can do is we can take the time domain signal and convert it mathematically into the frequency domain. Okay? Does that make sense? Do you have any questions about that? So, how do we do that? Okay? Okay, so now, to understand this, I'm going to draw another picture similar to this. I'm going to skip the sideways one. I'm just going to draw the top view. Okay? So it's a two-step process. Okay? So what we're going to have is we're going to have our magnet. We're going to have our sample. We're going to have our radio frequency transmitter. And then we're going to have at 90 degrees, and this is not perfect, but, and when I say, I mean literally physically 90 degrees, okay? We're going to have our receiver. So do you see it's pretty similar? But what we're going to do in step one is we're going to blast this thing So we're going to create a radio signal that has all the frequencies. Now, if we were to listen to it, it would just sound like static because it would look like this. Okay? It would just look like that. Okay? Just boom. And we just do a big, powerful pulse of that. Pow. For some period of time. And then we shut it off. And part of the whole subtlety of the NMR experiment, you can change the amount of time, blah, 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 right? Okay, what's going to happen then is the frequencies that are absorbable will get absorbed. The sample will get excited. Okay, when we shut it off, then the excited state thing are going to release and be measured. Okay. So this is also noise, but it looks different. It looks different in two ways. First of all, it has an underlying complicated pattern, okay? The other thing is that it gets smaller over time, okay? Now, this process is called relaxation. And the signal that we get is called a free induction decay, or FID. And most of us just call it the FID. Now okay, so imagine we blast the sample, we shut it off. Now the sample starts radiating energy back off. It gets smaller and smaller as the energy dissipates, but we're measuring the frequency of that. The frequency of that is not all frequencies, it's only a few frequencies, but it's coming in this complicated wave. So then what we do is that is actually supposed to be calculated, and I don't think there's supposed to be a dash. The FID is the time domain signal, right? In other words, we're looking at all the frequencies as they oscillate in time. So we start with this complicated signal coming down here, right? Decaying in this way. This is our FID. We do the FT. Sorry, we don't do it. The computer does it for us. And what we get is we get something that looks like this. Actually, I'm going to exaggerate the noise. And I'll show you why in a minute here. We get something that looks like this. Right? The computer is saying that this wave is made up of all sorts of waves of these various frequencies, some of which are just these random frequencies from noise, and some of which are much bigger. They're the actual peaks for our spectrum. Okay, does that make sense? So we like blast everything, and then we look at what we get back, and then we sort it out and say, we got this, we got this, we got this, we got that, so forth. Okay. Now, why is that so useful? Well, it turns out there's a couple reasons, but the most awesome thing about this okay, I don't have a lot of space here, so I'm going to just squeeze this here. So I'm going to give you an example. It's a made up example, but imagine we have something like this. Okay. So again, this and that, these are noise. And then this is a peak. and this is a peak. These are the frequencies we want to see, right? So you can see that they just barely stand out from the noise. Let's say that this was only one pulse. Well, what we could do is we could do a whole bunch of pulses, add the FID all together, and then do the Fourier transform. So it basically improves by the square root of the number of pulses. So if, for example, we do 16 pulses, the noise would be 1/4 of the height. You still have noise, but I'm just going to kind of sort of estimate. So 1/4 would be about this big, but the peaks would still be their maximum height. Because the noise over time tends to randomly cancel out. In one pulse, a certain frequency will be high, but in another one, it'll be negative or low, and it'll cancel out. So that if we did 100 pulses, we might actually get something that looks like this. And if you look carefully at our NMRs, that's kind of what you see. You see the baseline is sort of this little squiggle. The peaks stand out from it. Well, that's because we were able to get the signals out from the noise. Okay? Now, in carbon then, what that means is even though our peaks are going to be tiny, in fact, actually, with one pulse, they probably won't even stand out from the noise. If we can do a whole bunch of pulses, the peaks will begin to grow in. And so even though we have a weak signal with Fourier transform and time, right, we can enhance that signal. Does that make sense? Okay, so almost all carbon instruments are Fourier transform instruments. When we get our NMR, which is on order, and because of supply chain we haven't gotten yet, but when we get it, it's actually going to be a Fourier transform instrument. Okay? And we will be able to do carbon NMR. It just will take longer. Okay? All right. So last thing I want to talk to you then about this is okay. So relaxation time is the time it takes, let's say no, I'm going to say it's the amount of time So it's the amount of time it takes for all the excited atoms to relax, release their RF energy, and return to the ground state. Now, this is going to sound, I'm going to make a sound. It's going to sound ridiculous, okay? But basically, on the older FT instruments, we used to put a speaker up because the FT signal sounds like a frequency. It sounds like, ooh, like that, okay? Like imagine some kind of frequency and it kind of modulates and whatever. And if you listen to it, it's sort of like there's a pulse and then you hear, pulse. You hear like it's really loud at first and then it goes down to almost nothing. So that's because the relaxation is a kind of a random process that has a half-life, like radioactive decay. And so, you know, there's a certain amount of time when half will have, and then half of what's remaining will have, so only a quarter are, and then half of what's only an eighth, right? And as that happens, it gets quieter, it gets less loud because less energy is being released. Does that make sense? And so what we want to do is in our acquisition phase, I guess I should mark that. This is called our excitation phase. This is called our acquisition phase. In the excitation phase, we're putting energy in. The acquisition phase, we're cutting out. And we have to set how long we're going to do that. And what we're trying to do is find a balance to where pretty much almost all of the nuclei have released their energy, right? We don't want to cut it off short because then certain frequencies, because they're longer, won't have as many parts in the wave, and then they'll show up smaller than they should be. But we don't want to make it too long because then we're wasting a lot of time. Okay. So here's the problem. Okay. So for hydrogen, the acquisition time is really short. It relaxes super quickly. So like a tenth of a second. I'm talking, these are real times. Like we pulse and then we wait, but it's like bing, 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 really fast. Okay. For carbon, on the instruments that I used, the relaxation time was about 4 seconds. So that meant we would go, you know, bing, bing. Can you see the difference? So it takes a lot longer to get a carbon NMR. You have to do hundreds or even thousands of pulses, and it takes 4 seconds of pulse. We used to have to set up some of our carbon acquisitions. If we didn't have a lot of sample, we would have to run overnight for like 6 or 8 hours. Whereas a hydrogen NMR, you could do a hydrogen NMR in like 2 minutes. Okay. There's another issue to this. I don't have the actual numbers, but basically, if we look, and I'll have to look, I have another book. I have a couple books I'm using as my references here. So this is primary, secondary, tertiary, quaternary. It's complicated by the fact that you could have other elements here, but if we just look at this, this has the fastest relaxation. This is the slowest relaxation. So now, if we have, if we look at a molecule, like this, where we have, look, we have a primary, we have a primary, we have a primary, we have a secondary, we have a tertiary. What we're going to see is that the primaries release their energy really quickly. So the beginning of the FID, it's going to be kind of diagrammatic, but imagine that we have our FID, right? It usually looks sort of like this. Like that, okay? Because the primary frequencies are coming out faster at the beginning of the FID, there's more primary. Then we see the secondary, and then even over here, the tertiary sort of start to dominate, right? So the problem is that if we cut this off too early, we lose the tertiary. Their peaks get really small, right? Because they haven't had, they've been releasing more slowly, and their frequencies might be longer, and so we don't see them as much. Does that make sense? So what does this mean? Well, what it basically means is we can't use integration in carbon-13 NMR, because the problem is that we have to pick a point where our FID has decayed some reasonable amount. Very often that point is before, like if we let it go for like 10 seconds, which some people do, then all of the excited atoms would have a chance to release their frequencies and be registered in the FID and therefore be converted. And we do convert the height of the peak or the area of the peak based on the intensity, but because we don't do that, what we see is if we try to do integration, the tertiary and especially the quaternary carbons have smaller signals than they should. So we don't get an accurate integration. Does that make sense? So this is kind of a long explanation of how FT works, but it also sort of explains some of the issues that we have for, overall. So we're not going to do integration in carbon-13 NMR. Okay. Now, I have one more thing to say about, it's a totally unrelated thing. Just take this and store it in the back of your head, especially if you intend to go to medical school. So you've heard of MRI. So MRI is magnetic resonance imaging. It's basically an instrument that lets us do three-dimensional scans of things like human tissue to get images. So it works it gives us outcomes kind of like a CAT scan or an X-ray or something like that, but it uses the NMR effect. So you guys, if you've ever heard of what an MRI thing is like, it's like this big enclosed thing that you have to go into. Well, that's because it's a big magnetic field, and then it makes this really loud noise, and that's because it's got these how can I put it? It has these two different, it's got a transmitter and then it's got a receiver that are moving mechanically back and forth. You're not hearing the actual radio frequency. We don't hear that, but you're hearing them move, whoop, 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 as they are coming in positioning, blasting, moving out of the way so the other one can receive, that kind of thing, okay? And then it's literally able to sort of measure the NMR. Now, what it's actually doing, it's not measuring chemical shift. It's not measuring integration. What it's measuring is relaxation time. It's measuring how long it blasts the energy. How long did it take for that energy to dissipate at that location in space that I wasn't getting any radio frequency? And the image is actually, they go, imagine you have a big graph, right? And you say, in this region, the relaxation times were, 2 milliseconds. I don't know what the actual numbers, but like in this region, they were like 4 milliseconds. Then over here again, they were like, I'm not really drawing a picture of it, but you see what I'm saying, right? You go to each XY location, you plot the relaxation time using different colors, and it begins to outline things. And the reason it begins to outline things is a couple things. The main thing being how can I put it? As I understand it, and I'm not an expert in magnetic resonance imaging, it really was only just being invented and put into place when I graduated from college and was looking at med schools. In fact, one of the med schools I interviewed at, on the tour, they took us and they showed us this window, this giant hole in the ground, how awesome it was. And I was like, that's an awesome hole, man. Like, no, this is where our MRI, or well, actually they called it NMR imager at the time, is going in. And then what happened was, because it had the word nuclear in it, everybody freaked out. And so they took the nuclear word off and just left it magnetic resonance. At any rate, then later on in some textbooks and stuff, I read about this, and it's basically the relaxation time. That's how it works. That's why relaxation time is significant, you see? So even if you're in medicine, if you work with magnetic resonance imaging, you're going to see this terminology. All right, so that's how the instrument works. Now let's talk about what we do see in the carbon-13 NMR, okay? Okay, now I tried to scan a thing out of a book and my flash drive blew up on me and I was right before class. So whatever, I'm going to give you a rough idea of what we see here. I'll be coming back with some real handouts about this, because I didn't have a chance to prepare them. But let me just give you an idea of what the carbon-13 NMR looks like, okay? So I want to start with chemical shifts because I think that's a fundamental thing. So the first thing that you notice, if you look at a carbon-13 NMR, is that the numbers are way bigger. And that is a consequence of the gyromagnetic ratio, which is this constant that determines sort of the relationship between the magnetic field and the frequency. And you don't need to worry about that right now. Maybe when I rewrite this someday, I'll include it. But basically, what you just need to know is that they're like 10 times as big, or almost 20 times as big, okay? Okay, so again, what we would see is we could put a standard in here. And the standard, again, so this would be the reference standard. And it would be this molecule. Okay, which is tetramethylsilane, or TMS. And again, on this side, we expect to see high electron density. And then as we go in this direction, we see electron density decreases. And then as we go in this region, what we see is both, well, over here we have E minus electron density plus magnetic effects. And in this region, we just have magnetic effects, okay? And we're going to talk about magnetic effects in the advanced NMR section because it's an area of NMR we haven't talked about yet. And it's actually really important in terms of what we see, okay? So what we see then is in this region up to about 50, this is basically like alkane type stuff. So CH3, CH2, all of that kind of thing. Okay. In this region, this is the area of alkane plus electroneg atoms. So if you recall from our proton NMR, we said, here we have things like this. And we were looking at the hydrogens. Now what we're doing is we're looking at the carbon inside them, but it should be similar, right? Whereas we had a region further over, remember this one, it was in a lot of our examples, right? Where we had that, right? We had carbon, hydrogens on carbon attached to oxygen. Well, we see the same effect, but now we're just saying carbon directly attached to oxygen. And one of the reasons why this number is so much bigger is that now the oxygen is acting through only one bond. Remember, we said the more bonds there are, the weaker the effect. And hydrogens are always going to be 2 bonds away, pretty much. But carbon can be literally 1 bond away. So we see effects here. So this would be oxygen, chlorine, fluorine, and so forth. Okay. In this region, it's like, I don't know, it's like a little bit above 100 to about 150. This is aromatic carbons. So literally the carbons of a benzene ring. And then in this region, and they're sort of, they tend to sort of split them. And you'll see that in the little, I did this diagram, and then I'm going to do another one that's like actually more specific numbers. But the problem is that there's so many different variations that actually what most of the time you do, if you're really trying to work it out, is you like add, there's like tables, you add this, you add that, and get numbers. Okay. But anyways, this is for C double bond O, okay, of acid plus derivatives. So acids, amides, esters. This is for specifically C double bond O of aldehydes and ketones. And there's just reasons for that. But like if you have a peak at 210, you definitely have either an aldehyde or ketone. Okay. There's another thing that we see in the spectrum a lot. I'm going to talk about splitting. I may end up cutting this a little short, but okay. We get a triplet at 77. And what this is the solvent. So we always run NMR in a solvent. The most common is chloroform with a deuterium. And it turns out the deuterium splits the carbon shows up here. We get this thing, the middle one is at 77. Okay. And so if it's running deuterochloroform, it's almost impossible not to have that peak because there will be a little bit of carbon-13 in the deuterochloroform, and then the deuterium will split it. You get that peak. And so in fact, actually, most of the time we don't put TMS into our carbons. Instead, we set the 0, not really a 0, we set 77 and then calculate everything relative to that. But okay, but it's almost always there. All right, does that make sense? So I'm just going to say a correlation table will be provided later. Okay, because I didn't have a chance to get it in there. All right, next thing I want to talk to you about splitting in C13. Okay, so first thing is Come on, come back. Hello, there we go. No, we didn't, and I will. Just give me a sec here, okay? So it is so rare to have adjacent C13 atoms in a molecule. Okay, so we just don't see carbon 13 to carbon 13 splitting, because most of the time, when you have a carbon 13 atom in a particular molecule, all of the other carbons around it will be carbon 12, because carbon 13 is so rare. Okay. But we do see hydrogen 1 to C13 splitting. This is called second order splitting because it's two different nuclei. Okay. Now, there's a couple things you need to know about that. First of all, the splits are very large. They're so big that they are like 20 to 40 ppm. So what I mean by that is if we had a carbon 13 NMR spectrum, if this is 100, this is 200, this is 0, and we had a peak at let's just do this. We had a CH2, okay? We had a CH2, and it was absorbing basically here at, let's say, 27. That would be a reasonable thing for that. But it was split. Well, it would be split like this. We would see this. We would see a smaller one like way over here. We would see a larger one like way over there. Okay, can you see how that, if you had a lot of those, it would get unbelievably confusing, right? So while on simple molecules, the splitting can be useful because it can say, oh, this signals a CH2 and whatever. On more complicated molecules, the splitting is bad. So okay, so how do we do that? Well, real quick, short answer is Okay, sorry, it's a long sentence there. This is why I like how these things type, but whatever. So we blast the sample, we blast it with the carbon frequencies, but then we just continuously run the hydrogen frequencies. So the hydrogen frequencies don't interfere with the carbon. They just cause the hydrogens to absorb. We blast it with so much that all of the hydrogens possible absorb. So they're totally saturated. They're all in the excited state. And as a result, they don't cause splitting for reasons we'll talk about in advanced NMR when we talk about why splitting works. Okay. So this is called decoupling. So what would happen then is then in the decoupled spectrum, there would be no splitting. It would just collapse down to one peak. Okay. And so then we would only just, we'd see a peak for every different unique equivalent type of carbon. Okay. All right. Well, you know what? I think that's probably enough about carbon-13 today, because we're going to pick up some more stuff about it as we do advanced NMR also. And then we're going to put it all together and we're going to use it to solve some problems and whatever. But that's the basics. And like I said, I'm going to probably try to rewrite this and re-record it, but at least for right now, I have something. All right.